nanohub.org.
Online simulation and more for nanotechnology.
Yeah, I'm Matt Pleil. I'm from the Support Center for Microsystems Education. We're located in Albuquerque, New Mexico, and I'm actually physically located on the South Campus of the University of New Mexico. And I'm going to talk a little bit about what we do at the SCME and some opportunities that are available to all our micro nanotech education community as well, including recently funded undergraduate research experience program that we received very recently as a supplemental to our SCME ATE grant. So I'm going to mention a little bit about what SCME does and a little bit about our history so you can kind of get calibrated a bit and what we have to offer and what we do. And then a little bit more detail about the URE new opportunities that we have. And then I'll mention a few other things that you can also consider joining. So we started back in 2004 at Albuquerque Technical Vocational Institute. That college changed its name to Central New Mexico Community College back in 2006. And in 2008, we moved to the University of New Mexico. University of New Mexico has always had very close ties with the ATE program going back to the mid-90s. And we provide access to our clean room and at no cost to participants. So over the years, we've developed a long list of educational materials which are available on our website. And we have lots of community college partners across the country, including PCC, of course, and Rio Salado, Ivy Tech, Lone Star, and a multitude of other colleges we've worked with throughout the years. So we have downloadable educational materials from our website. These include PowerPoints, PDFs, and those sorts of things. We also have a YouTube channel that you can go to and use the presentations in your classes or have students watch them in a flipped classroom environment. And we have a series of asynchronous short online courses at our scme.online website, which you can also find through our main Support Center website. And we do have hands-on kits we developed over the years. We still have several available. So if you're interested in that, make sure you contact me and you can learn more about that. The image you see on the right there is a display of some of our hands-on kits that we can send to you and you can use in your classroom. So we have kits around Wheatstone bridge, thin film, interference, and the pressure sensor process kit, as well as we do have videos that we can supply you on micro nano fabrication and also nanotechnology that Ruth Carranza put together. So we also support the Micro Nanotech Education Special Interest Group. This started back in 2011 with a Micro Nanotech conference, annual conference. Deb was part of that and Bob was part of that. And then Abe Michelin joined us later on with Neotech, and Peter joined us from Shine. So, and now of course PCC supports this group as well. And over the years, we've grown it into a special interest group. So we do online meetings pretty much on a monthly basis. You're welcome to join the community. You can go to the MNT-EC.net website and fill out a form on the homepage, and then that will add you automatically into our distribution list so you can get invitations to our meetings. And if you have trouble with that, just shoot me an email and I'll get back with you and help you with that. We also work with industry closely, and we have an industry map project, so you can look at what industries are in your neck of the woods, and it's a really good resource for educators. And now we're getting contributions to the industry map from our other partners, as well as SemiWorks and Mansef. which are industry groups for those of you that don't know those acronyms. We provide professional development and have been over the years. We do outreach as well locally with our high schools and our high school teachers and students. Recently, I did a RAIN session, and you can ask Bob Ehrman about RAIN with the Boy Scouts of America. So, you know, we try to get kids interested as well in micro nano technology. And we try to do professional development with both high school and community college instructors. So we want to support faculty and professional development. So the image you see here is taken from one of our workshops that we did at the University of New Mexico several years ago. Adrian Seborn is describing the pressure sensor model kit to two of our attendees, one of which is from Shine. Alyssa, who you may know. And we also do fab tours, and I've started doing virtual fab tours online to STEM education groups, and that's kind of fun, running around with my iPad showing them the fab. And I think the kids like it, so we've done that as well. So the bulk of this presentation, we're going to talk about the undergraduate research experience, which was recently funded. On the right, you can see one of our workshops. This is a group of instructors. Most of them are from Erie Community College. And we have one student participating as well in this photograph. And that you can see them all dressed up in their clean room garb and having a good time. So, you know, you learn a lot in these clean room experiences. And we primarily target two-year instructors and faculty as well as technician students. So our primary partners currently under the URE is Lone Star College, which is also a sub-awardee on our current grant. And that includes Danny and Pamela. Danny is primarily focused on biomems and biotechnology. Pasadena City College, of course, is Jared Ashcroft. He's more in the bio-nano and nano realm. Ivy Tech, we've got Caitlin and Andrew, and they're in engineering technology primarily, and they also teach about MEMS and microsystems as part of their program. And then we have Rio Salada with Rick Vaughn, who has online courses available for MEMS and micro nanotechnology. But those are our primary partners under the URE Research Experience grant, but we have a lot of space for other people. So if you're interested, please let us know. You can come with your students. That's what we prefer. So the instructor comes with the students, and then they both learn in the clean room. And we'll get you some more details on that. So the key components of the URE supplemental grant is we're going to do some recruiting this semester. So we're trying to get our students together, and Jared just mentioned that he's in the process of doing that. I know Caitlin's doing some outreach to her students and trying to collect some interest. We have a wide range of topics the students can choose from, whatever they're interested in. We do some evaluations. So we have a professor from the Learning Sciences Department here at UNM that's going to observe and look at how we do it and give us feedback on how to improve these opportunities moving forward. And then Andy Bell is going to help us do some 3D mapping with his colleagues at Ivy Tech, and he's got a Second Life island as well as part of Ivy Tech's engineering technology program that he's building up and having his students contribute to. So that looks really cool as well. Okay, so like I said, we're recruiting students this semester. Next semester, the students will be doing some online work, and that's dependent on the faculty that's directing them at their home institution. So the involvement of the faculty is critical in this URE experience. We have online short courses for the faculty and for the students, and we're hoping they start in the spring of 2021. And then in the summer, we hope that everybody can come to the University of New Mexico for the clean room experiences. So we'll do probably 5 or 6 one-week sessions, and we'll be focusing on different things in all of those sessions. Okay, so if you look at the graphic here, the detail on the bottom row shows that online we have some biomems, educational materials, and Danny Kiner from Lone Star College will be heading that work. We have some online foundational work, as I call it. I'll be working on that with the other colleagues. And then in the summer, we'll have that clean room experience. So we will start with the MEMS overview, which is an overview of the applications and history of microelectromechanical systems, so they can get a baseline of what microsystems are all about. And then they can choose different areas of interest based on that. So there's lots of different topics they can do. So as I mentioned, Danny will be working with biomems, but Dr. Jackson, Nathan Jackson, who's a new addition to our group, he's a professor in the mechanical engineering department at UNM, and he's got probably 15 years experience in applications in biomems. So, and he's been teaching fabrication methods to his students. And then myself and Caitlin are going to be teaching fabrication topics to the students. Dr. Jackson and Andy Bell said that they would be open to mentoring students on modeling. So we do have access to some very sophisticated software called Coventerware. And so we can get students to access that software and be able to learn a little bit about modeling and designing in microsystems. And then we have an online safety course that's required of all students to complete and faculty before they come to our activities in the clean room. So we like to, get everybody oriented and get them all front loaded before they arrive here, so we can spend more time in the clean room working with the materials and executing on our designs and our research projects. So there's lots of topics the students can choose from. Of course, we got fabrication processes and characterization associated with that. Photolithography, wet and dry etching systems, deposition, which includes sputter, evaporation, and CVD, which is chemical vapor deposition. We also have opportunities for students to do some electrical characterization, learn more about MEMS design principles, device applications, biomems, flexible electronics. The modeling, I know that Andy's been working on cantilever and pressure sensor modeling on CAD systems, so the students can learn a little bit about how the model interacts with the actual fabrication. And then when they come here, they can actually try different metals, different materials, and see how it compares to their modeling. And metrology is measurement, of course, and so we have scanning electron microscopes and things like that that the students can also get access to. And then Danny is doing a lot of the DNA sequencing stuff, and there's a lot of micro and nano technology involved with that. So I'm not an expert on that, so I'll refer all questions on that to Danny. This is a snapshot from the Second Life Island that Andy Bell developed. That's me flying around. I don't know why I picked that avatar, but maybe I think I have more hair. But you can see some snapshots from there in the series of images, from different scenes on the Second Life. So Andy's had his students put their posters there, so you can go and view the posters and read about what they've kind of research they've done. So this is another opportunity for students to interact with each other as well. So we're hoping that students from one school will interact with students from another school, which would be really great, because that's similar to what we do in industry when we work on international teams or teams with other companies as well. Okay. So online, of course, we have all of these different courses. Here's a list of all the biomems classes online. We, of course, have overview and applications and biomolecular applications, therapeutics, diagnostics for biomems, clinical techniques and microtechnology, MEMS for environmental and bioterrorism applications, cells, DNA overview, DNA to protein, and DNA microarrays. So these are all short courses students can go through. Several of these were written by Linnea Fletcher, Celeste Carter, and Trish, is it Phelps, from Austin Community College several years ago when we first started out. So they were instrumental in helping us develop these curriculum. And Danny now is adding to it and updating some of the materials as well. So on the online foundational work, right, we've got the history of microsystems, introduction to sensors, transducers, actuators. We have a unit on career pathways for microtechnology, so if students don't understand what kind of jobs are available, they can go through that unit. It's a good way of introducing them to this micro nanotech world. And we, of course, have units of weights and measures and comparison of scale units, because many of our students don't understand angstroms, nano, and all of that. So we've developed some curriculum there, and we kind of give it focus or through the lens of micro and nanotechnology. And we do a little bit on SPC, which is statistical process control, and problem solving for microtechnology. So those are some of the units available. These are the online short courses, by the way. And they're asynchronous, so you can either send your students there and then talk about it in the classroom and do a flipped classroom thing. You can download the units and put it in your own learning management system and do it the way you want to, which is fine. We don't mind. We're not going to dictate how you should teach these concepts. Then we have fabrication, a series of fabrication units. So includes photolithography, deposition, etch, and then an overview of micromachining, specific pressure sensor process that we actually do in the clean room. It takes about 4 days to go through when you come here. And that unit is a requirement if you're going to do that before you come. And of course, MEMS making micromachines and crystallography for microsystems. So there's a little bit of material science involved in that. The safety and clean room protocols unit is a requirement before students come. So on the left image, you can see the title page to the PowerPoint. Everybody can get access to that. And then the right figure shows an excerpt where we talk about HEPA filters and show a schematic of a clean room and how we keep it so bloody clean. And we'll go through that in detail when students come here, when we give them our tour. We have a lithography unit, and there's a snapshot from the title page of the PowerPoint. You can see a photo mask also in that image, and on the right side is a snapshot from one of the learning modules, the reading materials, where we talk about spinning on photoresist and measuring the thickness of the photoresist across the wafer. So it's a very applied approach. And I came from industry, from the semiconductor industry, so I was training technicians how to do this stuff when I was at TI and at Philips Semiconductors. We have an etch unit. Again, on the left is an image of the first page of the PowerPoint, and the scanning electron microscope picture within that image shows a high aspect ratio folded spring, a leaf spring. So MEMS devices are microelectromechanical systems, so there's usually a mechanical component to it. So we do things like make inertial sensors, surface acoustic wave sensors, and things like that. And they all have different kinds of mechanical structures associated with them. So that's what I like about this field. It combines electronics and mechanical systems. And then on the right side is a snapshot which discusses release etching. So as you layer different materials together, you've got to put some space between them, some scaffolding material. And when you're all done, you got to remove the scaffolding so the parts can move. So that's the general gist of that slide. And of course, you have to deposit different materials as we're making these devices. So on the left is a slide which shows a chemical vapor deposition tool and how it works. And on the right side image is showing a design of an activated microcantilever, okay, and then all the different layers that are involved in making it. And when you work on design, you usually use software, CAD-like software. So the software images here come from Coventerware. And one of the first things we teach students when they're learning how to design is how to make a hinge on a micro scale, which is a lot harder than it looks. So there was a fellow by the name of Pister who patented the Pister hinge, which is basically the hinge you see here. So when the students learn about design, if that's what they lean towards, they'll learn how to make masks, how to design for the different mask layers, how to design to a specific process, because you can't just pick and choose anything you want. You have to understand who's going to make this for you and what do they have available. Okay, and then they go through and they can do a cantilever example, a pressure sensor example, learn about metrology structures that are needed to monitor the process as you go through the different process steps. So there's a lot you can teach the students just around this if that's what they would like to do. So here's an example of modeling in Coventerware where the student is determining the displacement of a cantilever under certain conditions. And another thing that we do is we make these Wheatstone bridge pressure sensors in our clean room to teach students about processing and about basic electronics at the same time. So on the left image there, you can see the pressure sensor as it looks when you're done fabricating it in the clean room. It's about 1 millimeter or so square. And on the right side, you can see what it looks like in a homemade package. So I'm looking forward to probably getting someone, perhaps at Ivy Tech, that's interested in packaging to take these little parts, put them in a package, hopefully put them in a circuit board, and then actually have a system that works. I know Andy Bell's really good at interfacing devices to Arduinos and LabVIEW, and the students love doing that kind of stuff. So they could actually either make their part and then integrate it with some electronics so they have a complete system. So you go from silicon to a sensor system. And that's a huge learning experience for the students as well. So we talked about the online prep work that students can choose from and do along with their faculty. And then we now are transitioning over to the clean room experience. So we can do several different things. We have some simple things we can do in the fab, which we call the art wafer. We have a pressure sensor process, which we've done for years. And that's a really good way of learning about the different processes and equipment. We have a newer device that the students can also make, which is called a bimorph cantilever. Dr. Jackson has worked on wearable electronics, which is starting to get more and more traction in the real world. And Caitlin and Andy are also interested in working on that with the students. And as I mentioned, we have biomems that Jackson and Kiner can lead. And this is in the clean room. This is when they come here in the summer. And Jackson's made some surface acoustic wave type of devices and acoustic MEMS devices as well. And we can do some of that here at UNM between our lab and his lab. And I can work with students on metrology and characterization. That's what I used to do in industry and as well as process characterization. So there's a lot of different things the students can decide to do when they come here. So the art wafer is a lot of fun. That's usually the first thing we do to get students oriented in the fab, how to use the equipment, how to use personal protective equipment and things like that. So we have an image of Christine from North Valley College in San Antonio. She and one of her partner students came out with the instructor several years ago and went through the clean room experience, and you can see her holding her art wafer that she created on the first day of being here. And on the right side is a close-up image of another wafer a student did from Central New Mexico Community College. She's now working in the MEMS industry, and she did a higher level art wafer, so showing two different thicknesses of silicon dioxide, giving the different colors. So the students learn about thin film interference and why different thicknesses of materials look to have different colors. So there's a lot of teaching you can do around that. So you've got, the photolithography, the etching, and all of that involved, as well as the oxide growth. And then there's our pressure sensor process. So the image on the right shows what the pressure sensor looks like from the back of the wafer, and then looking from the top down on a probe station. So you can see the anisotropic etching of the crystalline silicon. You can see the thin silicon nitride membrane, and then the Wheatstone bridge that's on the opposite side of that membrane as you're looking from the back of the wafer. This is a simple two-mask process, but you can learn so much in this process. We do, backside patterning, so you've got to align the front side pattern to the backside pattern, which is something that no one in semiconductors knows how to do. So I learned this after I left semiconductors. We do silicon nitride deposition and etching. We do a lift-off process as well as a pattern and etch process, sputter deposition, anisotropic etching, and then, of course, characterization with the probe station. And we also can put these devices on our scanning electron microscope. So this shows a snapshot of several images from our clean room of the different deposition tools we have. So on the left side, you have the sputter tool. We have a 5-gun sputter tool. It can do RF sputter, DC sputter, and pulse DC sputtering. So that allows us to put a large variety of materials on the wafer. This has kind of replaced our evaporation tool because it's easy to use, and we can pick and choose what materials and what alloys we want to use to deposit. So one of the things I'd like to do with this tool is, if Andy Bell and his team models different pressure sensor Wheatstone bridge thicknesses and materials like copper, gold, nichrome, that sort of thing, we can actually go make those devices here with the different thicknesses and designs, and then he can compare, his students can compare the actual device characteristics with the modeled ones. And that would be an awesome URE poster or paper to present. The other deposition tool we have is a Parylene coater. This is used a lot of times with biomems because Parylene is biocompatible. The body does not reject Parylene. So that's why a lot of devices are coated with Parylene. And there's other uses of Parylene as well. Dr. Jackson's the expert on Parylene. He's used it for a multitude of different applications over the years. So I'm looking forward to learning from him on more things about Parylene. And then on the bottom right side is an image of the Steed furnace where we do our oxide growth. And so, we can grow different thicknesses of oxide and whatnot and have the students characterize that as well. This is our lithography bay showing the different pieces of equipment in the lithography bay. So on the upper left is our coat station. So we have a spinner, which is on the left of that image, and we can spin wafers up to 6,000 RPM. This allows us to vary the thickness of the photoresist. And next to that is the soft bake plates, where we can do the soft bake after the coating of the wafers. And then moving on to the right, you see our 1X contact printer. It's a Carl Zeiss. Basically, it's an aligner, so we can transfer patterns from a photo mask to the actual photoresist on the wafer. And it also allows us to do backside alignment, as I mentioned earlier. Moving on to the bottom right image, you can see the caustic bench where we do our develop. Develop is a basic solution. So when light interacts with photoresist, with positive photoresist, it generally turns that part of the photoresist into a slightly acidic material. And when you put that into a base solution, the acidic parts will react with the base, and you can remove the photoresist where the light has hit. So it's kind of like developing photographs in the old days, but I can't use that analogy anymore because the students don't know what a darkroom is and what developer is and an exposure tool. So, you know, just us old folks understand that. So when I teach the faculty, I use the darkroom analogy to explain it. And then finally, after every chemical step, we do spin, rinse, drying. That's the final image there. It basically looks like a glorified washing machine, but it's really nice because we use deionized water to rinse any residual chemicals off the wafer, and then it spins at about 2,000 RPM, and we flow warmed nitrogen gas in there to dry off the wafers. So the wafers are constantly cleaned after every step in the process because particles can damage the integrity of the mechanical systems as well as the electronics circuits. We do have some reactive ion etching as well. This is some of our dry etching tools. So on the bottom left is our March reactive ion etcher. If you look up the model number, CS1701, that's the Starship Enterprise. So a little trivia there. And you can see it's kind of looks like the Enterprise on the front. So I always like to point that out to faculty and students. But basically we use that tool to etch silicon nitride, oxides, and do some descum to move residual organics that might be on the wafer. On the right side image is a picture of our Alcatel deep reactive ion etcher. This tool is about $750,000. And all it does is make really tall, skinny holes, right? So the upper left image is a scanning electron microscope picture taken after a pattern has etched into the silicon wafer. And you can see something that says S with Mike in that image. We diced that across that wafer so we could see the aspect ratio, but that says thanks, Mike. And that's part of one of our metrology masks, and we were paying tribute to Mike Lisecki, who was my mentor when I started all of this ATE stuff back in the day. And then there's an inset in that image of the scanning electron microscope showing the edges of that tall, skinny structure that you see on the right side. And it shows the scalloping pattern. And the reason it's scalloped like that is we switch between two gases. One gas system it results in the etching of the silicon. And then the other gas system we switch over to passivates the sidewalls. So you get the scalloping effect as you go down the edge and as you're drilling into the wafer. What's really cool about the deep reactive ion etcher, if you don't do it perfectly, you can create what's called grass, which are really tiny, tall, thin spikes of silicon, and it looks black. They also call it black silicon. So the solar guys are real interested in that because it traps all the light that hits it. That's why it's so black. So we can purposely make black silicon as well if somebody comes up with a cool application for that. And then, of course, we can do some electrical probing in our clean room. This is a photograph of our probe station. We can do up to 5 probes on it, and it also is integrated with an interferometry tool. So the students not only can probe their devices and see how they respond, but they can measure the deflection of the device in the z-axis and count the fringes to determine the change in the z-axis or in the z motion of whatever device they're looking at. So we like to put the pressure sensor in there, and then you can see what the curvature of that membrane is as we activate the device or as we change the pressure on the backside of the wafer. So the students get to play with this when they come to our fab, and we would love to do a little bit more with that tool and utilize it for the students' learning. This is a snapshot of the bimorph cantilever, so students are interested in making these devices. This process isn't fully vetted yet, so it doesn't work really well, so it's a great opportunity to help us improve the process and then characterize the results. And again, it's a simple 2-mask layer process to make these devices. Dr. Jackson has made a multitude of different biomems devices over the years. There are 2 images here. The upper left image is an energy harvester, so it's basically a mass on a cantilever. And as the mass moves, you change the capacitance of the system, and you can actually create electrical signals and store it so that later on you can power sensors. So he's done work with a similar device on powering pacemakers. The idea there is you don't have to open the person up every 5 to 7 years to replace a battery. So he's made some nice headway on that. And he did that work when he was in Ireland at the Tyndall facility for 11 years. And the bottom right is a microfluidics device. I'm not really sure what that is used for, but hopefully if you join our community, you can ask Dr. Jackson and he can tell you more. And I love metrology. You know, I like measuring things and making sure equipment operates properly. That's kind of my thing. So you can see the image on the right is that of a digital mirror device. These are produced by Texas Instruments. And this is a good hook for students because they all go to movies, or they used to. And the movie theaters all use DMDs now. It's all digital in the theaters. So it's based on this device, this Texas Instruments digital mirror device. Another trivia point is Texas Instruments actually got an Academy Award back in the 90s for the development of this device, and Lucasfilms were the first ones to make movies on a digital platform. But they had to do both digital and film at the same time because at the time the producers didn't want to have only digital because there were only 100 theaters back then that could actually show the movie, so they knew they wouldn't make any money on it. And as I said, we also have thin film measurement tools. We have a profilometer, which is a micro-sized atomic force microscope. Instead of looking at individual atoms, we look at micron scale structures. Okay. And when we characterize processes, we have metrology masks. So the pattern you see on the right is just a bunch of lines and dots or pillars and slots. And the students can see how the pattern from the mask translates into a photoresist pattern, which translates into a subsequent etched pattern in the substrate that's underneath the photoresist pattern. And they start to make the connection on how these things all interact. And there's a ton of experiments we can have them do to understand how to characterize processes. So you can use these structures to verify that the integrity of the design will be consistent. Okay. So I'm going to wrap it up pretty quick now. We have other opportunities for all of you. Many of you already know about our mintisig.net website and group. So please sign up if you have not done so already. And this group includes folks from all the ATE micro nanotech centers, as well as high school teachers. Some industry folks attend these meetings, and it's growing every year. We're at about 260 registered folks, and maybe 60 of them are active. So we get 20 to 30 showing up to each of the meetings, depending on their individual schedules. We also have working groups. So we have an outreach group that Billy heads. We have a curriculum group that Marco Corelli runs or leads, and an industry group that Caitlin and I are part of, and Todd Christensen, as well as Jared, and a professional development group as well, and others that I can't think of right now. But, you know, it's up to the group and the community to decide what we're going to work on. So our mission is to foster collaboration between educators at all levels, industry, and agencies for the relentless improvement of micro and nanotechnology workforce. So Mike Lasecki helped us write that. I think the relentless improvement came from him, which is really good. And coming very shortly in October is the COMS 2020 virtual conference. You can register on comsworld2020.com. These folks have been around, maybe 10 or probably 20 years or so. It's run by Mansef. And in fact, at the Edmonton conference way back when is where I met Deb Newbury. And that was a fun gig out in Edmonton, Canada. But yeah, you meet a lot of people, and they're all a bunch of entrepreneurs, mostly industry types, mostly small to medium-sized enterprises. There are some big companies represented as well. And now they're instead of just focusing on micro and nanotech, they're focusing on emerging technology, IoT, and things like that as well. And they're actually running their conference in parallel to the ATEPI conference, and there's going to be a lot of overlap and synergy between those two conferences. And then the other group I work with is ATME, which is the Association of Technology Management and Applied Engineering. The reason I hooked into this group is because they don't know much about micro and nanotechnology, so I'm trying to evangelize MNT to them. They're more classic, welding and machining and management and that kind of thing. So we're trying to get them more involved in micro and nanotech. And it's been a battle, and it's been a tough fight, but I'm the VP on the MNT focus group, and we're trying to grow it. Andy Bell participates in this group, and Mike Lund from Bemidji also participates in this group as well. So we're trying to grow it. And that's not a bad conference either. And they're actually doing it in association with IAJC, which is more internationally oriented. And most of the folks that go there teach undergraduate engineering and technology classes. And that's all I got. So how'd I do on time? Wow, 40 minutes, 45 minutes. But I can, answer any questions you have now.
All right. Yeah, thanks, Matt. That was awesome. Are there opportunities for undergraduates to engage in research for an extended period of time, providing them with a more in-depth experience, Matt?
So yes, right? So this year, they're going to start online to get the foundational stuff, right? So they can actually think about some kind of research topics they want to do. And then in the summer, they can come and do that. And then they go back to their home base and they write it up and they make posters and whatnot. And they can come back the following year to do a higher level version. That's our intent. Or they can come back later in the summer. Or they can spend 2 weeks back to back, and build on their expertise. So, characterization is something that technicians do all the time. So they can characterize something and then write it up. So that would be one example. So I'm hoping next year to submit my last support center proposal, and I want to include the URE in that very heavily. And then hopefully we'll get funded for 4 years to do that kind of thing. So we can continue this, and then students can come back, and then maybe even come back during the school year on their breaks and that sort of thing to work on projects and build on their research skills. So, yes.
Matt, this is Mel.
Mm-hmm.
I wanted to say I really appreciated your comment about the dark room and the developer, because that is so true, that we have found that when we talk to our students and we're talking about manufacturing plants from the past, they have no clue. They have no concept or frame of reference of what we're talking about. They see the cleaner ones and the automated ones and all that. So, but your comment was so spot on. It was so funny because I can relate to that.
Well, what's really good about our clean room is we don't have super automated equipment, right? So the students have to handle the wafers. They have to look at them with a microscope. There's no automated inspection tools and that kind of thing that you would have at an Intel or a Global Foundries. So they don't get that opportunity when they go into industry. They put a wafer in a big shiny metal box and it comes out the other end, and if it's screwed up, you know, they don't have that organic sense of what's going on behind the box for a long time. But going through even a 1 week thing in our fab, they learn maybe 60 to 80% of the concepts and principles, and then they can build on that with the specific equipment and processes for in their future company. So that's the intent.
And I've had people, this is Tom, that have come from the university world and come into industry and come in with, they have all the great credentials and everything from their education, but because they don't have that hands-on experience like what you're teaching in your lab, you know, it really takes them a long time to come up to speed on what these tools are really doing to the wafers and the process and things that's going on. And it does take a lot of hand-holding to get them through. Because they'll come in, the textbook tells me it should do this. Well, in the real world, it doesn't quite always work that way. So
to your point, at the University of New Mexico, Dr. Jackson and I teach a lot of hands-on stuff in the clean room. So I teach a fabrication course, which is all in the lab. There's very little lecture. And then the students have to present on what they've done in the lab, and they work in small groups and teams. So we're actually submitting an innovative graduate education NSF proposal this month to do just that. And I tell you, the technicians I've taught over the years, when they finished our program, they knew more than the engineers, and they came up to speed much faster, and they were well sought after. It's just we didn't get enough students in the program, and that's
right.
That's a problem we all have in technician education.
I had a question on your clean room. How large is that clean room? It looks fairly big.
We've got 4 bays and 4 chases, and I think it's about 7,000 square feet, something like that. So yeah, we've got quite a bit of tools.
A lot of equipment, tools and things in there. It looks great.
Yeah, it's a lot of fun. We have a dicer too now, so we can dice the wafers up, and we do have several companies that use our clean room. So we got 3D glass solutions, Biodirections. Biodirections is cool. They make a sensor that can detect when someone gets a concussion. So, and they're highly accurate, and it only takes a few minutes to get the results. So, and they do some of their work in our clean room, and then they have their own facilities to do other work. Oh, I see Rich is on the line. He was one of the, I think you were in that picture, Rich, weren't you? Or no?
Yes, I was. I was in the way farthest back.
Okay. Yeah. So we have a celebrity here.
Yeah.
So what did you think about the clean room experience? Was that worth your time?
Yes. Yes, it was for us because, well, I don't know how many people know, but we have a clean room here at ECC. Now, ours is a teaching clean room. You have more of a university clean room. So that was great for us to see some different equipment and hopefully try to expand our horizons here in our own clean room, even though we have, our equipment is smaller. Our equipment is not as many pieces as you, but we have quite a few pieces of our own, just we don't have all the capability as a university. So yeah, it was a good experience.
Well, I'm glad to hear that. Thank you for that. I'll put you in the commercials.
Awesome.
Matt, you have a couple more questions in the
Yeah, a
chat.
couple more questions.
Oh,
Go
okay.
ahead, Billy. Billy, go for it.
So Kendra wants to know, is there a way to get a list of the local industries shown on the SCME map without having to click on each individual one and write down the information?
You might be able to download the Excel file directly for each map, but if not, we can send that to you. So I can put you in contact with my colleague, Jennifer Nez. She's actually maintaining the maps for me now. And she can send you the most recent Excel file for that. But then it's a snapshot in time, right? If we add or update it, your file will slowly move away from the current one. So, but yes, we can do that.
And then there's another one from Kendrick. He wants to know if you can share the link to the site with the asynchronous learning modules.
Well, it's just scme.online. And then our support center is scme-support.org.